Welcome to today's instructional video on applications of quadratic functions. We're going to look at how to apply maximum and minimum value properties of quadratic functions to a variety of application situations. Okay, just going to look at our first example. So we're going to essentially look at two different types of problems. In some problems, the quadratic function is going to be provided, like you can see in this one, or there will be others where we will have to read the question and create the quadratic function on our own. So in this one, it's talking about a ball that's being thrown in the air. Its height in meters is given by this function that you see here. And then you can see you're asked a variety of questions about this particular flight path of the ball. So the first one says find the maximum height reached by the ball. Now, we're studying quadratic functions, so just to refresh your memory on quadratic functions are parabolic in shape, so they're going to look either like that, or they're going to look like this. And if they open down, you will have a maximum value at your vertex, and if it happens to open up, you'll have a minimum value at your vertex. So when I look at this function, based on the knowledge we've already accumulated, I see that it has a negative in front of the coefficient of my t squared, which tells me it is a quadratic function that opens down. So it is going to be modeled by this pattern. So if the height is modeled by this function, and I'm asked for, the keyword in this question is maximum height. So when I see maximum height, I immediately think vertex. So if you see in a question, find the maximum or find the minimum, you should instinctively be thinking vertex. So we're going to take this quadratic function, which is right now in standard form, and we are going to change it to vertex form, which we've gone through in prior videos. So I'm going to factor out my negative 4.9. My calculator going here. So I'm going to take 14.7, divide that by a negative 4.9, and it goes evenly 3 times. So this is going to give me, subtract 3t plus 3. Now in this example, there's decimals in the original function, so rather than go to fractions, we probably will go to decimals here. So we're going to take half of 3, which is 1.5, and we're going to square it. So 1.5 squared is 2.25. So now remember that whatever you put here, you have to multiply it by any coefficient. So I have to take 2.25 and multiply it by negative 4.9. 5 multiplied by 4.9, 11.025. Now that would be a negative, right? Because it's a positive 2.25 multiplied by negative, so it's negative 11.025. So to offset that, at the end, I'm going to add 11.025, which will give us a net change of 0 on that right side of the equal sign. So now my height at any time t is negative 4.9. Square root of the first, sine of the middle, square root of this one, squared, 11 and 3, so that's 14.025. Vertex. So my vertex is going to be at 1.5, comma 14.025. Alright, so at this point, I'm just going to go over here. So here's your regular vertex form. Y equals a on x minus h squared plus k. And our vertex is h, comma, k. The h is associated with the x, and the k is associated with the y. So what I get students to do at this point is now interpret this vertex. You can't just stop here. That's great that you've done the background work, but now you have to show and indicate you understand what this amounts to and how it will help you answer the question. So the question is find the maximum height. So I got to say which of these two numbers is associated with the height. So in this vertex, rather than an xy vertex, you just look here to get your variables. It's a t comma height function. So instead of x, it's t, and instead of y, right, y is normally here, well now in this function it's a height. So I just see which variable has been inserted in which place. So I'm looking for the maximum height, which means it's this number. So to answer the question, the max height would equal 14.025. We are in meters. Okay. Next question says, how long will it take for the ball to reach the maximum height? So think about what we just found. We just found that we had some ball that was following a parabolic path, like so, and it reached its vertex up here at 1.5, 14.025, where instead of just a regular generic x scale, the x scale is time, and the y scale has been replaced with the function height. So therefore, when you get your vertex here, it's t comma h, which means that this is the time it reached the maximum height. So the question says, so there's no work to do here, it's already been done up here. How long will it take for the ball to reach the maximum height? It will take 1.5 seconds. How high was the ball when it was initially thrown? This will often throw students off, but the key here is initially thrown. That is, in a roundabout way, telling you that means the time was 0. So it'll say in the beginning, when it was first thrown, when the path started. Those are all indicators to fill in 0 for t. So all I have to do here is basically find the y-intercept. So I take my original function, h of t was negative 4.9 t squared. I go back to standard form because that's always an easier one to get your, I think it's 14.7 if I remember right. Yep, 14.7 t plus 3. So all we're going to do is now insert 0 for t. So it's going to give me 0 plus 3. So at t equals 0, so this is the height evaluated when time is 0, you would get a height of 3 meters. Now just to kind of map this out, it says approximately how long was the ball in the air? Well, the ball started at 3 meters up in the air. At 1.5 seconds, it was at its maximum height. This isn't really a scale, I'm just going to give myself a visual here. So it was there, which would mean that if I go another 1.5, using symmetry, so if I go to 3 seconds, this is time in seconds, it should be at that same starting height. So this would kind of map out the path of the ball. So it says approximately how long was the ball in the air. Now, we don't have all the details, so I don't know whether the ball would, they could have been just a person standing, let's say here, 3 meters up in the air on top of a building or something, threw the ball up, come back down, and they caught it. This is what I know. I know that at 3 seconds, it'd be back to where it started. Now, if you want to call that the ground, well, then the answer would be 3 seconds. If they threw the ball up in the air, and then they just kind of let it go, well, then the ground is down maybe lower than the 3 meters, so it would be, if my answer to that question would have to then account for that last little bit of time it would take for the ball to keep going and hit the ground. And we'll get into more of this when we do our quadratic equation section. So we're going to just say approximately 3 seconds, just based on us mapping out what the whole problem looked like. Alright, so that was our first example where the quadratic function was provided to model the problem. Okay, let's have a look at what we got here next. Oops. So this next one, if we just kind of look through, it's talking about the number of board feet in a 16-foot long tree is approximated by the model. So you see there's a quadratic function provided again. Now we have to make sure we understand what the variables represent in the function. So it says where capital F is the number of feet and D is the diameter of the log. How many board feet are in a log with diameter 12 inches? What is the diameter that will produce the minimum number of board feet? So I want the minimum number of board feet using this quadratic function. So again, keyword, it's right there, minimum. So if you're studying quadratics and you see the word maximum or minimum, your brain should instinctively think vertex. So this is going to require us to figure out the vertex. And then we'll interpret the vertex at the end. So here we go, f of d equals 0.77 d squared minus, remember you always have to factor out your leading coefficient, so 1.32 divide that by 0.77 and I get 1.714. So remember, carry 3 decimals. 1.714 d plus, leave room, subtract 9.31. We're going to take half of this number and square it. Divide that by 2 and square it. 0.735. And then you have to multiply that by your coefficient that's in front, which is 0.77, giving me 0.566. That would be a positive, so I'm going to subtract 0.566. And that will give me the following quadratic function. 0.77, square root of the first, sine of the middle, square root of that, which would have been my 0.5, no, 0.735 square, just taking the square root of that, so 0.857. Try this again, 0.857 squared, subtract 9.31 minus 0.566, 8.744. Give me a vertex of 0.857, negative 0.8744. so we've arrived at our vertex, and we're going to interpret now. I don't really like the looks of these numbers, but we'll talk about that in a second. So this vertex this time, so instead of, again, remember your vertex is normally an xy ordered pair. However, in this function, it is D is where the x is, so this would be your D. And this is where your y normally would be. Well, your y is over here, so y in this case is your capital F. That's what I mean by interpret. I always suggest you write something like that in these application questions, so you interpret your vertex properly. Now the question is, what is, how many, oh, there was 2 questions, so I missed one actually. I went right to the second one. So we're answering this one right now. We'll answer the other one in a moment. It says, what is the diameter that will produce the minimum number of board feet? The only thing I don't like here is I'm getting a negative for the board feet, which seems like an odd situation, because you would, I mean, 0 would probably be the smallest amount of board feet you could come up with, but anyway, we're just going to go with the function and what it spit out. So it's telling me that a diameter, because that's what D stood for, a diameter of 0.857 inches produces the minimum. Okay, so that's the second question, this one here that they asked. The first question says, how many board feet are in a log with a diameter of 12? Well, this one just wants us to fill in D equals 12. So you can either go, let's just call it number 1. Let's go back to the very original. So it wants you to fill in a diameter of 12. They gave you the diameter. It doesn't say anything about max or min, so it's not asking you about vertex. So it's 0.77, 12 squared. Subtract, get my original function here, 1.32 times 12, take away 9.31, and I'm going to get 0.77, 12 squared, 1.32 times 12, subtract 9.31, and that is equal to 85.73 board feet. 85.73 board feet. Now you can see we're able to answer these questions not having any idea what they even mean by board feet. We could research that a little further if we were in class. We probably would kind of have a look at what do they mean by board feet, what does board feet measure, etc., etc. Anyway, we're just going to work with the math of the function and answer the 2 questions that they asked. So there's the answer to the first one. And then this is the diameter of a 16-foot log that would produce minimum board feet. So again, what I said I don't like about that is my answer is a negative board feet. So how that would get interpreted, I'm not really sure. All right. Okay, so we've got one more. This one has the function provided again. So again, great time now to, after having watched a couple of examples, try this one on your own. And then I'll go through the solution here and you can have a look and see how you made it. The path of a thrown baseball can be modeled by the function given. H is the height of the ball in meters. D is the horizontal distance of the ball from the player in meters. What is the maximum height reached by the ball? Alright, so the key word there, max height. Hopefully your brain says vertex. So we're going to put this in vertex form. Negative 0.004 gets factored out. Divide 0.14 by negative 0.004. and I get 35. D plus 2. So half of 35 is 17 and a half. And then we're going to square that. That's going to give us 306.25. However, that then has to get multiplied by our leading coefficient to give me a negative 1.225, which means I'm going to add 1.225. And now write out our vertex form. So height equals square root of the first, sine of the middle, square root of this one, so it opens down, which will give us maximum. That's good. So my vertex is at 17 and a half, comma 3.225. Interpret your vertex, and what do these two numbers mean? X is being replaced by D, which is the horizontal distance. So basically what they're talking about is they got somebody here throwing a ball like so, where horizontal distance and then how high the ball is in the air is the y value. So the y value is being replaced by the height of the ball. So to answer part A, what is the maximum height? The max height would be 3.225. You must always put units on questions like this where they're talking about units. You have to put units. So it's the height of the ball in meters. There's the answer. What is the horizontal distance of the ball from the player when it reaches the maximum height? That's this number then. So I'm not going to do any more work to do part B. Part B, it was 17 and a half meters. So the ball was over here, 17 and a half meters when it reached its apex, its highest point. And then finally part C, how far from the ground is the ball when the player releases it? So this goes back to like that first example. It's basically saying in the beginning. In the beginning means, if you recall, normally we say make time 0. Well, this one isn't time, it's this number. So make this number 0. It's basically saying find the y-intercept. So I'm going to let d equal 0. Well, let's go back to the original function, then it's really easy to do that. So if d equals 0, your height is going to be 0 plus 2. There's how high the ball was when it was initially thrown, 2 meters above the ground. Okay, so there's another example. Working through where a quadratic function was provided. However, there was context, meaning words surrounding the problem, that we then had to interpret and use to solve and answer some questions. Alright, and now, finally, we arrive at the ones that sometimes can be the most challenging. However, they are great problem-solving skills to kind of dig at that deep part of your brain to make you think at that most analytical level, where all you have is words. There is no quadratic function in the question. We're going to interpret the words and turn it into a mathematical function. Hopefully, based on the fact that we're dealing with quadratics, we end up eventually with a quadratic function that we can then use to answer the question. And the whole idea here is that when I see this question, find two numbers whose difference is 13 and whose squares when added together yield a minimum. Well, there's one word in that whole statement that is the key, and it's that one right there. Now, when I say key, I mean key in regards to getting us pointed in the right direction. Obviously, there's some other very important words in here as well, but minimum makes my brain think quadratic that looks like this. There's my minimum at that lowest point, the vertex. So in the first three examples, that was relatively easy to do because the function was given in the question. So this is the challenge of this one. Well, here, let's start by saying, well, I wonder what those two numbers are. I don't know what they are. If there's something you do not know that you'd like to know, use what are called let statements. Let's let x represent the first number, and let's let y represent the second number. Now, let's see what they tell us. There's two things that they tell us here. The two numbers have a difference of 13. So I know that if I took x subtract y, I'm going to assume x is the bigger number. I'm going to get 13. Somebody else might write y subtract x equals 13. That would be fine as well. They'll just have y come out to be the bigger number. We'll end up getting the same two numbers. So this is going to be important in a moment, but right now that's not a quadratic, so that's not something I could put in vertex form and find the vertex. The key is now to build a function to model the quantity they want you to minimize or maximize. So this one, I want whose squares when added together yield a minimum. I'm just going to call it S for squares. Well, the squares of each of these numbers would be x squared plus y squared. There's the squares of each numbers added together. I want this function to be as small as possible. So if we look at this and say, well, at least it's starting to look quadratic, what would be the dilemma that we'd be faced with here that's making this not kind of fit the mold of what we dealt with, let's say, in the last three examples? So hopefully you'd look at it and say, well, there's two different variables on the go here on the right side. We've never dealt with that. And you're right, we have not. So that's where we have to somehow use other information in the question to fix this problem, the two variables. I do not want that. So what I'm going to do is go to this little piece of information I have here, and I'm going to rearrange it. I'm going to say x has to be 13 plus y. I'm going to take that and then put it in here instead of the variable x. Now you could have rearranged for y equals instead and put something in here. It doesn't make any difference. It'll just be a different, you'll either find number x or number y. Okay, so let's do our substitution. So s equals will stay the way it is. Instead of x, we're going to put 13 plus y in its place. And then everything else will just stay the same. Now, how has that helped the problem that we were discussing here, Bart? My dilemma here was I had two different variables. Well, that dilemma has been cleared up now. I only have the variable y on the right side. So let's take and expand this out and turn it into a quadratic. So 13 squared is 169. 13 times y and then double it would be 26y. Square your y, oops, plus y squared, plus your other y squared that was already there. And now we're at the quadratic function s equals 2y squared plus 26y plus 169. Well, we started with a couple of sentences at the top. We have now used those sentences to model, this is called modeling, to model a quadratic function, where in this case, well, what's y? Y is the second number. So what we're going to do is go over here now. Because I want the minimum, I'm going to see what y value makes this function, which represents the sum of the squares, right? Sum of the squares. I want it to be as small as possible. So we're going to go s equals 2y squared plus 13y plus, still have our plus 169. So half of 13 is 6.5. 6.5 squared is 42.25. 42.25. Multiply that by 2 is going to give me a positive 84.5. So I'm going to take away 84.5. And we will end up with s equals 2y plus, so I want the square root of that, which is 6.5. 169 minus 84.5. Is 84.5. Should know that. 84.5. Vertex negative 6.5, comma 84.5. Like before, interpret. What do these numbers mean? Well, this can get confusing because this is usually where our x is. So our x is really our y value for this problem. And our y value, which always associates with this value over here, is really our sum. So this is your minimum sum. And this is the second number that gives that minimum sum. Now the question, I believe, asks for what are the two numbers. Yeah, find the two numbers. So I got one of them. One of them is negative 6.5. So students say, well, how do I get the other one? It's right up here, look. X is the other number. Well, x is always equal to 13 plus the y value. So if the y value is negative 6.5, x is 13 plus a negative 6.5, which would give me positive 6.5. So the two numbers are 6.5 and negative 6.5. And if you were to, those are, they differ by 13. If you were to take 6.5 and square it, and negative 6.5 and square it, that would be the smallest possible sum you could ever come up with for two numbers that differ by 13. And we were able to model all of that through this quadratic function that we were able to create. Alright, so there's your first example of taking words and turning them into a quadratic function. Alright, on to another example. So when I look at this one, I'm trying to find maximum area. So very early in the question, I know what kind of function I need to build. I need to build an area function. That's the only way I'm going to get the maximum value of area is if I build an area function. Often in some of these questions, a sketch might lend itself to point you in the right direction. So I've got a triangle. I'm just going to draw a triangle, any old triangle, and I want the sum of its base. So this is its base. I'm going to use b for its base, and this is its height, let's say here. Well, it says that the base plus the height has to equal 13. Right? It says that right here. Sum of its base and its height is 13. Well, now I want to manipulate these numbers in such a way so that this triangle will have maximum area. Well, let's start with the function that would give me the area of this triangle. So the area would be 1/2 the base, which I've called letter B, times the height, which I've called letter H. Well, that certainly is not a quadratic yet. So much like the last function, we're always going to try and get a single variable here and a single variable on the right side. Right now I've got 2. That's why they give you this other piece of information. Now sometimes they call that a constraint. It's some other kind of limiting factor in the question. I'm going to rearrange this for h equals. H is 13 minus b. So I'm going to go over here and I'm going to replace h, right, the letter h. We're going to put 13 minus b in its place. Area is 1/2 the base. Instead of height, we put 13 minus b in its place. Well, let's expand this out and see what we end up with. So area equals half of 13, so 6.5 b, and then minus 1/2 b squared. So we should be pleased with the result because we've got a quadratic with a negative in front of the b squared, so it opens down. So to answer the question for max area, I just need to rearrange this new function now that I've created and put it in vertex form. A equals, factor out your negative a half. So we're going to divide 6.5 by negative a half, so that's going to be minus 13b plus take half of 13, which is 6.5. 6.5 squared. We just did it, but I forget. 6.5 squared. 42.25. That needs to get multiplied by your negative a half. We're at negative 21.125, which means I've got to add 21.125. Here we are in vertex form now. Negative 1/2. Square root of the first, sine of the middle, square root of this one, plus 21.125. Write out your vertex. So my vertex is 6.5, comma 21.125. Now interpret your vertex. So this is normally our x, but our x is in this problem being replaced by the variable b. This would normally be our y, but instead of y, we're talking about a. So this vertex is b, comma a. I was asked determine the maximum area. So it didn't ask for the dimensions. I don't need to figure out b and h. It just wants to know what is the maximum area that this triangle could take on. Well, we just figured it out. It's right here. 21.125. That number is the maximum area. It happens when the base is 6.5. So the max area is 21.125. What units are we working in here? I think it's in meters. No, centimeters. So this would be, because it's area would be measured in square centimeters. And there you have it. So we started with some measurements and some criteria about a triangle, and we turned it into a quadratic function, which we then modeled and put it in vertex form to identify the maximum value. Alright, another one. So this one's talking about a rectangular corral. So a corral is something they use to keep livestock in on a farm. Is to be built, and you've got 70 meters of fencing. So if the fencing has to enclose all 4 sides of the corral, what is the maximum possible area of the corral in square centimeters? So I think for this one I'm going to draw a diagram. So I've got a corral. I don't know what the measurements are going to be for it, so that's where you bring in unknowns. Let's call it x and y. I want maximum possible area of this corral right here. Well, let's build a function to model what I want it to be as big as possible, which in this case is area. So the area of that rectangular corral is xy. Pretty standard problem that we've encountered in the first 2 examples. There's 2 variables here. I don't like that. So there must be some other way, some other information given, so I can eliminate one of these variables. Well, let's bring the 70 meters of fencing into play. So if you're going to build a corral like so, and you've got 70 meters of fencing at your disposal, and you want it to have maximum area, well, that would probably mean you're going to use all of the fencing, which means if you went x plus y plus another x plus another y, that should add up to 70 meters of fencing. So let's write that out as a math statement. 2 x's plus 2 y's should give you the length of your fence. Now let's pick one of the variables. It makes no difference which one. Let's say I rearrange and get y equals this time. So 2y would be 70 minus 2x. To get y by itself, divide everything by 2. Y would equal 35, take away x. This is going here for the variable y. So here's our new function. Area is x times y y being 35 minus x. Expand that out, have a look at it. 35x, take away x squared. So let's see, what do we think of this? So it's quadratic, I like that. It opens down, that'll give me a maximum. That all makes sense, so I think we're in good shape. So let's take now, and we're ready to, this is part A. We're ready to now put this in vertex form. So factor out your negative. So this would normally have been a plus 35, but it's going to switch to minus 35x. Right, that times that would give you your negative x squared, and negative times a negative would make your positive that you're supposed to have here. So take half of 35, which is 17.5, and square it. 17.5 squared is 306.25. But that's going to get multiplied by a negative 1, which will make negative 306.25. So to offset that at the end, you would want to add a 306.25. Vertex form will look like so. Negative bracket, square root of the first, sine of the middle, square root of this one, all squared, 306.25. My vertex is at 17.5. 306.25. Interpret, what do each of these numbers represent? So this is your A, and this is your X. You say, what's the heck's X? Look at your diagram. That's why you have to have clear diagrams so you know when you bring variables into a question, what do those variables represent? So I can see that X is this length right here. Let's go back to part A and see what they asked. I don't know if we've answered it yet. So in part A, if the fencing has to close all four sides, what is the maximum possible area? So in this one, they're asking me for the maximum possible area. So part A, the maximum possible area is that number right there, 306.25. The measurements were in meters. Area would then be in square meters. Now I'm just going to move this question here. So part B says, in part A, what are the dimensions of the corral with the maximum possible area? So now it wants the dimensions. The dimensions are the x and the y. Well, I have one of them, correct? I have the x value. So the x value is 17.5. So to do part B, what I need is, I need the y value. Well, it says right here, y is 35 minus x. So y is 35 minus the x value at that particular instant, which turns out to be 17.5. So actually it turns out that it's a square. So my optimal measurements, actually when you do this stuff later on in calculus, that's what we call this. We'll do it again later on using calculus. It's called optimization. Optimal meaning maximum or minimum. So the measurements that give us this maximum area would be, just want to get my eraser here, would be x would be 17.5 and so would y. So it would be 17.5 by 17.5 meters by 17.5 meters. Let's just make sure that's 70. So 17.5 times 4 is 70 meters. So that means I've used up all the fencing. Alright, so that's part B. So it was just taking my answer in A and interpreting a different value in the vertex. Now, part C says if the corral is built with a wall of a large barn as one side and the fencing enclosing the other three sides, what is the maximum possible area of the corral? So this is another common question you'll see. So rather than needing fencing on all the sides, you only need it on 3 of the 4 sides. So let's have a look at what this looks like. So now, so part C, so you've got some kind of a barn or something here, it said. So you don't need to put any fencing along here. You only need to put fencing out here, across here, and down here. So now let's say this is x and this is y. Well, that's still x over there. I still want to get max area, so I want my area function, which doesn't change. It's still xy. Now this is where things are going to be a little bit different. Rather than 2x plus 2y, I don't need anything over here, so there's not going to be any y. It's going to be 2x plus 1y will equal your 70 meters of fencing. So now it's probably easier to rearrange and get y equals, which is 70 minus 2x. So that's the only thing that's going to be different. Rather than the 35 minus x like we got last time, we're going to get 70 minus 2x because there wasn't the second y. It's not two y's, it's only one length of y fence. So my new function will be x, 70, take away 2x. So I get negative 2x squared plus 70x. We want maximum, so vertex form. So we're going to take half of 35, 16 and a half, square that, which, 17 and a half, which is 306.25. Multiply that by negative 2. Which is, oh, that's not what I wanted, sorry. 306, so it should be what, 612.5. And I want that it's going to give me negative, so I'm going to have to add 612.5. Area equals negative 2, square root of the first, sine from the middle, square root of this one, all squared, plus 612.5. Vertex is at 17 and a half. 612.5. Alright, so part C said what was the maximum area under these new criteria? Well, this is your area, and this is your x. So, max area would be that number, 612.5 square meters. So you can see that it's now much bigger, which would make sense because you don't need to put as much fence on that one side to close it in. So part D said what are the dimensions? Well, there's one of them, that's your x. So in this case, y is 70 minus twice x, which is 17 and a half. So that's 35, so y turns out to be 35 meters. So this field should look like this. The y actually, which one's the y in my picture? Let me have a look. I think it's the long side across. So if this is your barn, you should go 35 meters here and 17 and a half meters on the two sides. There's your dimension. That's what your field should look like. And that would give you a maximum possible area of 612.5 square meters. Okay, so the next one we look at, it's going to be very similar to the last couple we've just done. It's talking about Chris, who wants to make an area, a rectangular area for a mulch pile. She wants to enclose it in such a way to use the corner of her backyard. She wants it to be twice as long as it is wide. The yard is already fenced. She simply needs to construct two sides of the mulch pile enclosure. And she only has 15 feet of material available. Find the dimensions of the enclosure that will produce the maximum area. So her backyard is already rectangular, something like so. She wants to put something in the corner, like so. It's a rectangle, which is x. What did it say? She also wants it to be twice as long as it is wide. So let's say, well then let's say this is x, this is your longer one, that has to be 2x. So the area area, she only has 15 feet of material, so area is 2x squared. This one's a little different because you're just getting this basic function here. I don't think we're even going to have to make a quadratic function. Because she's only got 15 feet of material available, there's really only one way this can work. So this is going to have to be, right, 2x plus the x has to give you 15. So 3x has to be 15. X has got to be 5. So the dimensions got to be 5 and 10. Right? There's no other way that would work. So there's one that, yeah, it was quite wordy and all, but so to find the dimensions that will produce the maximum area, so the dimensions, the only dimensions that work, so my dimensions, this one I didn't even have to get into quadratic function, vertex form, nothing, would be 10, what are we in here, feet, by 5 feet. And the maximum would be what? So if x is 5, 50. Didn't ask for the maximum area, but that's what it would be. So that one was really, really easy. Well, sometimes what happens with a question like that is we just get caught up in all the words and just can't get our brains to wrap around what it is they're telling us. But that one worked out very, very nice because of this whole thing and giving us that x and 2x bit. Alright, on to the next. This one's got a bit of a different spin on it. So this one will get into looking at economics and finances and money and how we can maximize the money we make from selling things. So make sure there's two different things we have to make sure we understand here. One of them is revenue. That's a term that might be new to some of you, versus profit. Okay, they're two different things. If you're running some kind of a business selling merchandise, think of it real basic like a hot dog stand. The revenue you make from selling the hot dogs would be the total money that you bring in from sales. Total money generated by sales. Versus profit is where you take the money you generate by your sales, but then you subtract your costs out of that. What did it cost you to buy the material? What did it cost you to pay your employees? Etc., etc., etc. And then anything that's left over is considered profit. So profit is essentially the revenue you make, but then you must subtract any costs that you have. And that's the profit. So this is more of what they call your bottom line. What are you actually making from the business? Alright, so the first example is talking about selling baseball caps with a logo on them. It said last year the store sold 600 of these hats at $15 each. The store manager is planning to increase the price. A consumer survey has shown that if they put the price up for $1, every time they do that, they're going to lose about 30 sales a year. Now, sometimes people will say, right, well, you don't want to lose sales. Well, sometimes losing sales can still allow you to make more money if you put that price up a little bit. So it's trying to find that balance point that'll give you your maximum revenue. So in these cases, what you have to do is you have to bring in a variable, and it's generally pretty much the same thing. So I'm going to let x represent the number of price changes. So like how many times am I going to change the price? And now I'm going to use that and the information up above. I'll just leave that so I can see. So imagine you were running this business and you wanted to get revenue. Well, the way you would figure it out is you would take the number of baseball hats that you sell and you'd multiply by how much you sold them for, your selling price. And that would give you your revenue. in these questions, there'll always be what I would refer to as an initial condition. So what was happening before this business decided to try and change things up? So I'm going to now start bringing in variables. So I'm just going to go, instead of writing it all out in words, I'm going to say, okay, R for revenue. What was happening before anything changed? So remember, this first bracket is the number of hats bracket. Well, they were selling 600 hats. So 600 hats. That's what they did last summer. They charged, so I'm just going to leave some room here. I'm going to put something in there in a second. And then what were they selling them for? Well, they were selling them at $15 a hat. Now, if you do the math on that, they were making $9,000. 15 times 6 is $9,000. $600 times 15 is $9,000. So they want to see if they can make more. Well, so this is where your variable comes in. X. Price change. So every time the price change, now don't lose track of brackets. This is your hats bracket. This is your price bracket. Well, they're going to put the price up. So the $15 is going to increase. I'm going to add to it $1 every price change. If these had been $3, if we're going to put it up $3 every time, then this would be 3x, $3 per price change. So this is how much the price is going up every price change. Now sometimes they'll do the opposite. They'll drop the price and sell more. You just have to read it properly. Then you'd put a subtract here. I'm just going to erase. So if they increase the price, they're going to sell less hats. So the number of sales is going to drop. So that needs to be a subtract. You say, well, how many sales are they going to lose? They're going to lose 30 sales every $1 increase, which is what these X's represent. So they're going to lose 30 sales every price change, meaning if they change the price by $2, so two $1 increases, they lose 60 sales. You've just made a revenue function. So now we're going to expand this out. Now remember, they were making $9,000. That's what they made last summer. Let's see if we can get them to make more money. 600 times 15, 9,000. 600 times x, 600x. 30 times 15 is minus 450x. Take away 30x squared. So let's tidy it up and put it in standard form, and then we'll get it to vertex form. Ooh, running out of room here. Alright, so my revenue will be negative 30x squared plus 150x plus 9,000. So revenue will be negative 30 x squared, take away 5x plus, leave room, plus 9,000. So half of 5 is 2.5. 2.5 squared is 6.25. Multiply that by negative 30. Calculator here, so 6.25. 6.25. Multiply that by a negative 30 is negative 187.5, which means I have to add 187.5. That's a good sign because this number is going to go up, which I want. I want to make more money. This is their revenue. Put it in vertex form. So revenue. Okay, sorry about that. I had a little glitch there with my computer. Froze up. So I'm back to where we were now. This is what our quadratic function looked like in vertex form. Remember that x was the number of $1 price increases. $1 increases. That'll be important here in a second. So my vertex is at 2.5, 9187.5. This function models R for revenue, which is in where the Y is, and X is the number of $1 increases. So this is saying to make 2.5 $1 increases to get to that maximum revenue. Well, that would mean we're going to put the price, so 2.5, that's the number of $1 increases. Remember, last year they were selling them for $15. So we're going to put the price up by 2.5 $1 increases, which would be $2.50. So increase price by $2.50. That doesn't mean charge $2.50. It means add $2.50 to what you were charging last year. So the new price this summer will be, rather than $15, it will be $17.50 a hat. They are going to sell less. We get that. They're going to sell how many less? They're going to sell 30, 60. They're going to sell 75 less hats than they did the year before. But they're going to make more money. If you take $15 at $600, that's $9,000. But if you take $17.50 at $525, it's $91.87.50. So even though they sold 75 less hats, they still made more money. So that's kind of this whole way you can try and work with a function to maximize revenue. What is the maximum annual revenue? That would be this number right here. So you should charge $17.50 to generate for you a max possible revenue under those conditions outlined in the question of $9,187.50. Alright, so that's our first look at a revenue question. Here's another one. So a bus company carries about 10,000 riders a day if they charge $1.80. A survey indicates that if the fare is decreased, the number of riders will increase by 1,000 for each 10-cent fare decrease. What ticket price will result in greatest revenue? So, like always, you're going to let your variable represent the number. Now, this number of 10-cent decreases. So 10-cent decreases. So if you're running a bus company and you want to figure out your revenue, it will be the number of passengers, and you multiply that by how much you charge them. So the fare, what are they paying to get on the bus? And that would tell you how much money you made off of that particular bus line that month. So let's build this in now with the information that's given. So remember, always start with status quo. Say, well, if I didn't change a thing, what would happen? I'd get 10,000 riders on the bus every day, and I would charge them $1.80. But I'm going to try and make more money by doing this. So remember, these are decreases. So the price is going to go down. Now you got to be careful here. It's 10 cents. This is in dollars, $1.80. So 10 cents is 0.10 for every price decrease. When I put the price down, I'm going to get more passengers on the bus. How many more? 1,000 a month. So I'm going to take my 10,000 and it's going to go up 1,000 for every 10-cent decrease. Expand, turn this into a function. So 10,000 multiplied by 1.8 is going to give me 18,000 minus 1,000 x plus 1,800 x minus 100x squared. Alright, let's tidy this up and get it into vertex form. Revenue will equal negative 100x squared plus 800x plus 18,000. Right, that's what they were originally making, this 18,000. So if x, meaning the number, if they don't make any price changes, they'd make what they used to. So let's see if we can figure out how to maximize this. So negative 100 x squared, subtract 8x plus 18,000. Half of 8 is 4. 4 squared is 16. 16 times 100 is negative 1600, which would mean I'd want to add 1600 at the end. Vertex form would look like so. Negative 100, square root of the first, sine of the middle, square root of your last one, all squared, 19,600. Giving me a vertex of 4, 19,600. This vertex interprets to be revenue and x. Remember what x is. X is the number of 10-cent price decreases. We're going to make 4 of them, which this interprets to mean drop the price 4 times, every time by 10 cents, drop price by 40 cents. This number is how much money you're going to make. So look, they're making more. They used to only be making 18,000. Now, under these conditions, they'd make 19,600. So that's another $1,600 they weren't making before. What am I asked? What ticket price will result in the greatest revenue? So ticket price was originally $1.80. We're going to drop it by 40 cents. So the new ticket price should be, so the new ticket price should be $1.80. Take away the four 10-cent decreases, so they should charge $1.40. And if they do, they will get less people traveling on the bus. However, they're going to get more people traveling on the bus. The fare has gone down, which means more people will then start to use the bus, but they'll make more money than they were by charging them more money. The $1.80 they originally charged. Those ones are just reruns of the ones I had before. So that gives you a pretty good overview of the different types of problems. So in this course, we're really going to be interested in these profit, revenue. Actually, none of these get into profit, but so for the most part, revenue questions. And also then we get into our area measurement questions like we did prior to these ones. Those are the ones where you have to create the functions on your own. All right. So hopefully you've had a chance now to work your way through these applications, and I understand that these can be a challenge. There's a couple of sets of practice problems in your class notebooks that you're now going to need to go and work your way through. Remember, you don't always have to work through all of the examples, but you certainly have to do enough practice to make sure you understand the material. So best of luck working on those. If you have any questions, please reach out at any time. I'll do whatever I can to help you and get you pointed in the right direction. And once we get through this and you're comfortable with it, you will contact me for a checkup, and we will make sure that you're comfortable and confident in the material.